Hey guys, Mr. Beckes here. Today we're learning about matter, atoms, and elements. What's the matter? It's all good. Yeah, that's right, I got jokes. So matter is anything that has mass and takes up space. So look around the room that you're in right now. Pretty much everything you see, some things you don't see, are made of matter. An example, your chair. Your chair has mass. It takes up space. It's matter. You have mass. You take up space. You are matter. Air, you can't see it, but it's made up of atoms. It's made up of oxygen and nitrogen and so on. It is matter. Think about a balloon. You blow up a balloon, air takes up space, right? It's matter. And water is another example. Matter is anything that is made of atoms. So let's talk about atoms. Atoms are the smallest units of matter. Again, matter is made up of atoms. Atoms cannot be broken apart without turning into a different kind of atom. More on that later. So atoms, anything you can see around you, if you break it down to its smallest possible part, it's an atom. Atoms do have parts of themselves. It's called subatomic particles. The three subatomic particles are protons, neutrons, and electrons. Starting with protons. Protons have a positive charge. They are located in the center of an atom, and that center is called the nucleus. So if you take a look at the little very simple diagram here, in the middle, the cluster of circles you see, that is the nucleus. You've got three positive circles. Those are representing the protons. And in this atom, we've got four greenish circles. They are representing neutrons. This would be one atom of lithium because there are 1, 2, 3 protons. Buzzing around the outside, we have the electrons. Moving on to the neutrons. Neutrons have a neutral charge or no charge. They are also located in the center of the atom known as the nucleus. Electrons. Electrons have a negative charge. They orbit around the outside of an atom known as the electron cloud. So these electrons are buzzing around the outside real fast. Electrons and protons have opposite charges to keep the atom balanced. So if the atom would lose an electron, it would then get a positive charge. If it would gain an electron, it would get a negative charge. The electrons and the neutrons could change. The protons always stay the same. If you were to change the protons, you would actually end up changing the atom altogether. An example, if I remove one proton from here, it gives me helium. If I remove another proton from here, it gives me hydrogen. If I remove electrons or neutrons, it changes the charge and balance of the atom, but it doesn't change what it actually is. I have a video explaining what I just said right here, so you can pause the screencast and watch this video in your notes. Next up, I want you to label the nucleus and electron cloud. So again, here's another simple diagram of an atom. The middle section, as you can see here, the cluster of protons and neutrons called the nucleus, and electron cloud is the area where the electrons are buzzing around the outside of the atom. I want you to think about something for a minute here. Look at the nucleus of an atom. Is the total charge of the nucleus positive or negative? So if you look at this case, I have 6 protons, 6 neutrons, and 6 electrons. If I'm looking at just the nucleus, though, the neutrons have no charge at all, so the nucleus is actually always positive because of those protons having a positive charge. Now, if you look at the whole atom has no charge. It's neutral because everything's balancing each other out. So the protons and the electrons balance each other out because those are the positives and negatives. Another video clip for you. Again, you can pause the screencast and take a couple minutes to watch this video. So when atoms join together, they form molecules. An example of a molecule would be 2 nitrogens stuck together would be a molecule of 2 nitrogens. O3 is also known as ozone, are 3 oxygens that are stuck together. When different atoms join together, they form something called compounds. And these compounds are how atoms build everything around you. Okay? So sodium chloride, sodium and chlorine bonded together makes salt. That's just table salt. Sodium is completely different than sodium chloride. Chlorine is completely different than sodium chloride, but they bond together and they make something completely new and different. Same thing with H2O. H2O is a compound. It's two hydrogens and one oxygen bonded together. Hydrogen is a gas naturally on Earth. Oxygen is a gas naturally on Earth. You bond two hydrogens and an oxygen, now you have a liquid at room temperature. Okay? So the properties change completely and change entirely. In fact, if I were to take H2O2 and add one extra oxygen, it gives me hydrogen peroxide, which is completely different from water. Atoms connect to each other by forming bonds. This is a special way that they hold on to one another. So that H2O, they're all stuck together from bonding, which we'll talk much more about later. I'm going to skip the break point for now. We're going to keep going and kind of wrap up these notes. So elements. An element is matter that's only made of one kind of atom. An example of an element is oxygen because it only contains oxygen atoms. So if I had pure oxygen, there would be nothing there but oxygen, and that's all that makes it. If you make water with oxygen, it's H2O. This is not an element, it's a compound. Another example, like gold, for example. If I have pure gold, gold is an element. If I break gold down to its smallest piece, it is one atom of gold. I add a whole bunch of atoms of gold, and it gives me a whole bunch of gold, which is an element on the periodic table. Again, the most basic unit of an element is the atom. All of the elements are listed on the periodic table of elements. You could think of the periodic table as the cookbook for the universe. Everything that's matter that you see around you is made up of different combinations of things on the periodic table. It is really incredible to think all the different things we have on our planet and in the universe, as far as we know, is all made of the 118 things on the periodic table. Here's a simplified version of the periodic table. You can kind of take a couple minutes to peruse that. It is organized in many different ways all at the same time. We're going to talk a lot more about that later. So how do we tell atoms apart? Like in the video that I just showed, you have to count the protons. The number of protons in an atom defines the element. The number of protons is also known as the atomic number of the element. If the number of protons changes, the element changes. An example would be nitrogen has 7 protons, giving its atomic number 7. Oxygen has 8 protons, giving its atomic number 8. If you were to keep adding and subtracting protons, you would change its atomic number and you would change the type of atom that it is. So by looking at, here's one block on the periodic table. This is boron. So if you look up here, I have the atomic number is 5, and the mass of boron is 11. So here's what that means. 5 is telling you the number of protons. It's also telling you the number of electrons. So basically, if this were a test question, you get 3 answers for the price of 1. This 5 tells you the atomic number, it tells you the number of protons, and it tells you the number of electrons all in one boron atom. The mass down here is 11. How they find the mass is they take the protons and the neutrons and they add them together to give you that. So that means they don't tell you the number of neutrons on the periodic table. They assume you could subtract these two to figure it out. So there are 6 neutrons in one atom of boron, 5 protons for a total mass of 11. Why don't they include the electrons in the mass? Why don't they add another 5 in there? Because electrons are super duper duper small. I know it's a super sciencey word, right? Super duper duper small. So it would almost be like you stepping on a scale and then a piece of dust falling on you. It doesn't even register on the scale. So electrons are so much smaller than everything else, we don't even count them in the weight, okay? That's all I have for you today. If you have any questions, just let me know. We're going to do a bunch of these types of examples next time.